Good day, folks. This is tutorial number 38, and I want to show you a few things about the icon joint force probe that appears in the mechanical systems experience where you are trying to do rigid body dynamics. Uh, when you go to this application, mechanical systems experience, and you select the scenario tab, what you see is this ribbon of uh, ribbon of icons, and the particular icon that you're interested in is called right here, Joint Force Probe, and it looks like that when you enlarge it. And as an example, I would like to do a problem of this type where you have a mass, that green ball up there, which is rotating about a base through this rod with an angular velocity omega. And what we like to do is to find out what is the reaction force at the base at this joint, which is a revolute joint, by the way, and the shaft. Okay. Now, first of all, I have separated these so that you can see what is involved. There are three parts. There is the orange base here. There is the rod, the gray one, and the ball, which has a mass of 10 kilogram. Dimensions are given here, and notice that what I have done is I have chosen the radius of this gray piece to be uh, very small, 2.5 centimeter, uh, just for visual purposes, because we're going to assume that this is massless. So I have to assign a mass very small. I can't assign 0, but I'm going to make it 0.005 kilogram. The dimensions of this base, which actually make the revolute joint, this orange base, are irrelevant, but these are the things that I'm going to be using. And just to show you how these are connected together, here is my revolute, as you can see, between the shaft gray and the orange. And here is the rigid joint between the shaft or the rod and the ball. Okay. Now, as I indicated, the orange base is actually stationary, so dimensions of it is irrelevant and the mass of it is irrelevant. However, something has to be assigned. Also, for that gray piece, that gray rod, I have a small fillet radius up there at the corner because I want to minimize my work and create that gray rod, by doing a rib operation. And you need some kind of radius up there to make it work. Okay. Now, uh, basic dynamics tells you that if this is going at an angular velocity omega, this mass experiences an inward acceleration that we call centripetal acceleration, which is the value of the mass times the length of the uh, rotation arm right there, which is L, and times omega squared. And if you plug in the values here, assuming that omega is 60 RPM, you're going to have 395 Newton. That is the virtual force or inertial force that the green mass will feel. And of course, that is going to appear here at the bottom as a force, and that is going to be the joint force. Now, what about the moment? Well, moment is going to be this virtual force times the moment arm, and the moment arm, it's reasonable to look at this diagram and say the moment arm, remember this force goes inward, the moment arm is that height, which is 1.5 meter. Uh, Unfortunately, the number that's calculated in uh, in 3D experience, it does not use the coordinate system down below. In other words, it does not use a moment R in this diagram 1.5. It does something else. I'll allude to it in a minute. So now, here's a situation, redrawn again. It creates a coordinate system and places it at some point. You can see where it places it when you run the simulation, but the documentation doesn't tell you where it is. So basically, to check the moment arm, you have to take this distance. You have to eyeball basically the distance from that horizontal piece all the way to the place where you see the XY kind of axis on your screen. And if you use that number, then of course it's going to match the things that CATIA slash 3D experience produces for you. Now, that's not good, and spent a lot of time trying to work it out and looked at the documentation, and it's not there. So anyway, we'll see. When you create a joint, create on the joint force probe, it asks you to select the joint. In our case, it's going to be that revolute joint at the very bottom, orange, between orange and the rod, the gray piece. And then you can display the results either as global, those reaction forces, either as uh, global XYZ or the joint, what is called joint frame. A joint frame is that thing that we don't know where it puts it. Okay. Anyway, now after I do that, I say a few words about a more complicated situation. This is a problem out of Merriam and Craig's book, and it says that this disk has an has a mass center which is not exactly at the center location, but it's offset a little bit. So it's basically the same problem that we did a few minutes ago. I mean, I described to you a few minutes ago. There's the lump of mass here, the gray, the green, the green ball, and instead of the disk, we create a lump of mass, 6 kilogram, and then it's turning. But here I have two basically supports. Okay, the one that I did for you did not have the A support, the top support, and everything works fine. Here, it may be tempting to do it something like that. You create another cylindrical joint here, and it works, except that you will see if you try to do this problem the way I described the present tutorial, you're not going to get the reaction forces at this point. Okay. Anyway, here's a solution out of Merian in case you want to try things, but I can tell you that it didn't work. All right, so let's go ahead here and we're going to make these things. I have an assembly. Let me insert my first piece here, which is going to be that orange base 3D part. Right away, I'm going to rename this thing. I'm going to call it orange base. Orange base. Let me do a copy here and put it there. Paste. All right, and then we say OK. So on the horizontal plane here, let me go ahead and go to part design. On that horizontal plane, I will sketch two circles. One of them is going to outer circle. The other one is going to be the inner circle. The other one is going to be the inner circle, and I use these dimensions that I have shown you here in the slides. So this one is the inner one is 0.025. Okay, and the outer one is going to be 0.05. 0.05 meter. Okay, there we are. Exit. And then we're going to pad this thing up by height of 0.1 meter, which is 10 centimeters. I'm going to change the color here also. Right click properties on the graphics tab. You're going to use orange. By the way, if these are elementary and simple for you, you can always fast forward until you get to the point where I actually do the mechanism and put the physics behind it. Okay, that's good. So now we go all the way to the top. Let's insert our shaft. So right click, insert, 3D part. I'm going to call this thing the rod, or what is rod or shaft? I'll call it rod. I'll call it rod here. That's the gray piece. Rod. Okay. So let's go to the part design and make it. I again use the XY plane, and on it I draw that circle. Let's see now. Where is this? Draw that circle of radius, this radius. But what I can do instead, I can project that inner circle and then proceed from that point on. There we are. So if you exit, you'll see that the circle is over there. And I want to use the rip operation in order to go up and then sideways. So in order to do that, while I'm in the rod design on that vertical plane, I will draw the center curve or the spine of that ribbing operation, which looks like this. I go from here to here. We'll dimension it in just a minute. Let's dimension these things. So for example, this is going to be 1 meter, 1.5 meters, and this is going to be 1 meter. There we are. And I told you that I'm going to put a small fillet there. So where are the fillets? Corner is over here, so I'm going to put a tiny 0.025. Oh, that's good. Very good. Now exit. Okay, so I'm going to rib that circle along that center curve. So the ribbing operation is right here. Okay, so let's see now. Sketch 2 is what I had right there. This is, actually, let me cancel that for a second. I have 2 sketches. Sketch 1 ribbed along sketch 2. So let me do a rib sketch 1 along sketch 2, and yeah, so there we are. Okay, we go all the way to the top. Let's create our green ball, green mass there. So we're going to insert 3D part, and I'm going to call this thing the green mass. Let me copy, paste it there. Okay, say all right. And what I'm going to do is I create a sphere over here. And one way to do that, let's go to that part, green mass part. I create a point right there at the center of the circle, a point at the center of the circle, and there's my circle. This point belongs obviously to the green mass, and then on that face, I will sketch half a circle, which we're going to shaft it in a minute, or revolve it in a minute. So for example, let's see now, half a circle, arc, and I'm going to close this. All right, let's dimension that. That dimension of that ball is totally irrelevant because we're going to assign the masses. Was that right? Let me see for a second. Radius 0.2, yeah, 0.2, very good. And exit, yeah, exit. And we have a shaft here. Where's that? Shaft, that sketch along that line. Okay, very good. And let me change the color here. Properties, graphics, green. Okay, so as I said, hopefully you didn't need the first 10 minutes of this video because it's just a matter of making these things. Now, let's go ahead and assign some constraints. So first thing we're going to do, we're going to make sure that this this orange base is fixed. So I'll do it from here. So that orange base is now fixed. You can see that. There is your constraints, assembly constraint. Now we're going to make a revolute between these two. So revolute, and I use this particular template, axis, plane, and control the angle by selecting two vertical planes. Select that. So it's going to be this axis and that axis. This plane and that plane. And for the controlling this, because I'm going to put some speed on it later on, some omega on it, I need two vertical planes. So I'll use for the orange piece and the rod, I'll use the two vertical planes. Okay, so see the two vertical planes is going to be used for that purpose. Say no. All right, now it's going to be, this ball is rigidly attached to that rod. So another assembly constraint. So where's the rigid? This is the template that I'm going to be using. That green piece and that gray piece. And say okay. All right, that takes care of the first part, making the model, creating the constraints, which are going to turn into joints later on. So let me collapse these. All right, so update to get rid of these. Now we're going to go to create a mechanism. We have to go to mechanical systems design. So you click on it, and the first thing we're going to do is actually to create the mechanism. Select the mechanical systems design tab, and then here's the mechanism that's going to be created. You can give this thing any name that you want. My rotating assembly mass. Say okay. Notice that it did create it right there, and the joints are created right there. And there's a command which is automatically also created because I made this thing an angle-driven revolute joint. Okay, it's there. Now the next thing is going to do assign properties, assign material properties. And when I say material properties, masses. So you click on the weight definition in the mechanical systems design. You click on the weight definition. Notice that everything is red, that nothing has been assigned. I did not put any material properties on it, etc. So let's go ahead and do it one by one. First of all, orange base, you click on it. It says click this hyperlink to declare a weight. I'm going to do that. Now, what I'm going to do, as I've seen in the other videos, I'm going to assign default properties of steel. If you select this checkbox here, it puts the properties of steel, but here I can use it or I can leave it the way it is. I have no problem, because remember, this is not going to rotate. This is going to stay put. So I can leave it like this, no problem. And then close that. Let's do the other one. So notice that here, this is now blue. Let's go to the rod. You click on that same link, put properties of steel on it, but this, I want it to be a massless rod, so I'm going to change that thing to 0.005 kilogram. You can't set it equal to 0. It's going to come back with an error message, actually. You click on it. The only thing that's left is that green mass. You click on it, assign weight, first put the steel on it, and then you change that thing, make it 10. Please note that I said that the dimensions of this ball, etc., don't matter, because we're going to put masses on it ourselves. Okay, and then when you're done, just close that. All right. Now, can we check this? By the way, you can check it by mechanism player. If you turn this thing around, notice that it does turn. That's a good sign. Reset. Say okay. Next thing we're going to do is to go to mechanical systems experience. You click. We don't want to create a mechanism. It's already created. Let's not worry about it. Say okay. You can give it a scenario name if you want, but that's okay. Now, what I'm going to do is this revolute joint here, I'm going to put a motor excitation on it. What that means, it's a fancy way of saying that, okay, let's go ahead and assign a velocity motor excitation. See that? Velocity motor excitation. basically give it the speed that you want. You click on it and just wait for this thing to pop up. It says, all right, where is that command? We already have a Revolut join. So join, we already have a Revolut join, and there is a command associated with it. It's this. Okay. So it says, if you had many of these commands here for different reasons, you select the one that you want. I want, there's only one command, and I select it. Now it says, give me the speed. So I'm going to make this thing 6.28 rad per second. Remember 2 pi? 2 pi, right? 6.283. That's where it is. Okay. This is 2 pi. And then we say, okay. Good. So we already have an excitation here. Now I'm going to assign my joint. See that? Joint force probe. I can do that now. I can do that later. But I'm going to do it now. You click on it. It says, where is the joint? Well, the joint is this Revolut joint. I want to find the force on that joint, on this. You select it. You can do it for the rod, or you can do it for the base. One is going to be negative of the other one. It doesn't matter. And notice that here I have two options. One is the joint frame, or the other one is the global frame. Global frame means give it to me in terms of XY, global XYZ coordinates. Okay. So let me do that with the global one, and then we say okay. So we have created a probe, joint force probe, which includes, by the way, torques, as you'll see, and there is a excitation, which was the speed of that motor there. Now we're going to create our dynamic scenario. It says that, well, you already have excitation specified, so we just use it. If you have multiple excitation, you choose the one that you want. And you have a probe, use it. And we're going to do it over 10 seconds. Now remember, this is going to go 10 times, around 10 times. The only reason I'm making it 10 times because I want to show you something. I want to show you where is that mysterious plane that is being created for us to estimate the moment arm. Now, I'll do a 10 because then I can move things around and you can see it better. And then say OK, and finally we're going to run it. See that? Right click, force. Now, notice that this plane is created down here, and the moment arm is actually the distance from that top point to roughly that place, okay? So if this thing was, I don't know, if this was 1.5 meter, it looks like the moment arm is about 1, something like that. Anyway, it's done. So we go to view scenario results. Deselect everything, but just show me X and Y and Z components of the force on that base. Now, first of all, if you plot it, two of them are going to be sinusoidal. The other one is 0. Force in the Z direction is 0. Okay? If you want numbers, you go here. 394, right? 394, and it's going to go to 0, and then it's, it's harmonic. So if you go 394, it's right here. Okay? Now, if you go and say, okay, show me the torque. Show me the torque. Again, two of them are sinusoidal. The other one is 0. Okay, in the Z direction is 0. If you want numbers, they're over here. And this 436 Newton meter, if you take that force and multiply it by that number that we eyeballed, the distance from here to that plane, you're going to get something right on the dot, very close to whatever I have here. All right, folks, and good luck in trying to do the same thing here, because if I did not have the cylindrical joint here, everything would be fine. But with this one, you will not be able to get a solution as you see down there. Okay? By the way, this is a reaction. Good luck. I'll try to do another one with this force joint or joint. I can't remember what is it. With this joint force probe is used.